Okay. So we look at the different models here, the PPE models, the SPE models, the parallel programming models for those of you that want to work on parallel models, and then the multitasking SPE and the self-software development flow. The first one, the focus of this one is why we need this kind of programming models. The massive computational abilities that we have under the cell architectures, and we have a huge communication bandwidth. We move data at the rate of 300 bytes per second. We move the data independently between the SPE and also between the other PPEs. Okay? Our resources are distributed. We distribute resources across different levels in terms of low level, like the functional components of our SPU or PPU, in terms of tasking, in terms of threading. While we're waiting for the fixing of this one, the programming model, you look carefully, right? We can have situations. The listing we have an ASPE, and then we have the models based on the memory requirements of the applications. So now you can tie up the memory models against the cell architecture. You can have a situation where you have your programs fit, the total of your program address space fit into the local store of one SPE. On the other hand, you can have that address space spreading across the EA's effective address of your main memories and also to your SPE as well. The other scenario where you have is that your address space of your SPU program here may be across different SPE, either to cover the whole 8 SPE or maybe across a couple of SPE. And then at the BE level, here's the case where you have the address space cover also the EA, the main memory here, and also the address space of the local store on different SPE. And then the last situation where you have the PPE threads running on different, on the PPE here, running at different instances of PPE. Let's take a look at the PPE programming model. We went through an example yesterday, very simple example, just to show you, you can build a PPU program. And that PPU programs will do nothing else but to control the executions of your SPU program. Control and managing that SPU is the key functions, the main function of these PPU programs. We provide what we call the CE-soft, the cell-embedded software format here, linkage formats, to allow you to refer to the same program using a symbolic name to refer to the same address space between the EA and the local store. So you don't have to do any mapping, you don't have to do any translation, you don't have to worry about 64-bit versus 32 bits on the cell here. Okay. The role of the PPE programs, of course, manage, locate the system resources as well as the cell resources. It will do the printf, the file I/O, all of those I/O requests for your programs. Do we have any things down there in the SPU to do any printing? No, we don't have anything. Right? All we have is just a vector machines running on some computations. That's all. Single SPE programs, we have a small small programming model and a large programming model. The small single SPE models, we refer to that model as a single task environment. It's small enough to fit into a 256 KB of local store. Sufficient for many dedicated workloads. How sufficient it is? What is the size of the program that you think that can run on the local store on that 256 KB? How many lines of code do you think that will run? 20 lines, 30 lines, 100 lines, 500 lines of code. You can run a program 500 lines of code on that 256 KB. Okay, so it is small, but not very small. That can accommodate a very large size program. Okay, and then we mentioned about the address space between the EA and the and the local store. There's a line that delimits the address space, and the mapping of that address space will be done by your MMU and the MFC. Everything's done for you by going through the DMA, and by going through some of the memory transfer functions. Go to the MMIO, for examples. Those will be translated automatically for you, so you don't have to concern about it. So in the small environment, small single SPE programming model, everything's be dandy, nice and dandy. The tool and environment, we give you the compilers, we give you some of the libraries, the linkings, the linker, the loaders that initialize, load, start, stop your program. So this is the typical environment that you have. Example programs for this environment, like this program here, we call the SPE_foo.c. So a C programs to compilers and then produce a binary called SPE_foo. We have an integer SPE ID, address 64 arguments, right? And then 64 bit of the environment pointer. We've seen this before, right? This is the SPE thread, right? And then we do something over here based on the argument that we pass here. Then we do printf, whatever, return 0 or return I. Now this is the PPU program. And we do the status, declare the SPE ID here, is the SPE_ID_T, do the thread creations, do some wait here, and return. We have to declare the program's SPE_foo, which is an SPU program, declare it as an external SPE_program handler_T. Seen that many times, right? That's basically, that is it. However, in a large program, what happens in the case where we have a program and that address space, is larger than the 256 KB? What are we going to do? And here, in this environment, what we can do is can partition the programs into different segment address space. We have the code segment, we have the data segment, we have only stacks, all right? And C soft as well. We partition into small pieces, and then we DMA the pieces that we need whenever we need to run on the DMA here, on the SPE here. Okay, the control of passing or breaking up or managing of these programs rests with the PPE. So here we use the PPE, breaking the code and the data into small pieces, DMA down to transfer the data down to the SPE program, perform some calculation, and return it back to the PPE. For I/O, we would do the same thing. For I/O, we DMA the data. For example, in this case, the int declared by the IP32 here, an array of 32 locations, and then 32 entries here. We feed it to the programs ops with function IB, with the argument IP here, perform the operation, generate the output, and DMA back to the system memory, which is the main program running over here. Okay, for those of you who send us, you telling me yesterday, right? You show me that every time I do the DMA, I issue DMA request, I wait for the data coming back some cycle later, and then I continue to work. What happened to that latency time? What I'm going to do while I'm waiting for the data? The scheme is said that, okay, we can provide you some sort of mechanism we call the software managed cache. Software managed cache is nothing else but a software implemented cache. Just the concept of the hardware cache that you had before in the architectures, we use as a small locations where we store some frequently referenced data in there. Okay, when we need the data, we go to that location, search for the data, right? And then if the data is there, we load that data. If not, then we generate something like the data is not there, some cache phone or something. We go outside, either the next level of memory or the next level of memories. We bring the data in. On the hardware side, we need to deal with cache replacement algorithms, the size of the cache. All of these organization, how do we organize the cache as well, right? How many lines of cache? How do we group that line of cache into? How many set of cache, right? The way that we organize the cache. We're dealing with the same here. However, here, we'll give you, as a programmer, the flexibilities of how to organize those cache. So once you decide the name of the cache, the type of data that you use in that cache, and what is the replacement algorithm that you use in this cache, you use the cache. You store the data here. Storing does mean that this cache will do the DMA for you. What DMA technique that this cache will use? Double buffering or command list or the form of DMA command list? You don't care. Like the implementer, the software cache implementer implement this scheme for you. All you need to know is that I have this data type, right? I define a cache and this data type. Okay, and I have this interface I call to load and read the cache or store the cache. Store the data in the cache or read the data out from the cache. And that's it. When I need the data, I go to this cache, then I supposed to have the data ready for me. Prefetching the data is another function of this software cache. How many software cache can I have? How many hardware cache can you have on your system? One, right? Can you say that, well, I don't like that cache. Can I replace that cache by different size or whatever? Can we? No way, right? On the hardware side, let's go to Intel. Say that Intel give me some scheme where I don't like that cache size, and the cache size and the line, the size of your cache line, and how you organize the cache. Let me make another cache. No way. Once the decision on the hardware side, once the decision on the size, how to implement that cache was made, you cannot change. On this end over here, you do have the opportunity to change the cache. The size of the buffer, which is the buffer, nothing else but the buffer, right? The size of the buffer, the data type you put in here, and the organization of the cache. Plus, on this organization here, how many cache can you have? On the hardware side, one cache. How many cache can you have? 2, 3, 4, 5, right? This depending on what? Subject to? But the size of your local store. Performance-wise, subject to some things that you have to live with. That means that you have 256 KB. You reserve some buffer for your software cache. The remaining for your instruction, for your data. And coming back, how do I know the size of my instruction and so on, through the linker and through some of the tool provided, option provided by the compiler, it should spit out, the size of our code segment or data segment, so we would know. So the programmer has a lot of freedom, right, to manipulate, to set up the cache, to set up the buffers down in the local store here. You want to use the raw DMA to transfer the data by yourself, fine, you do have that option. You want to use some option already provided to you to do the DMA for you, to get the data for you, use the software cache. Here is at the low level API, we provide some of these functions. We call the low level API, where we define the cache missing, the line, the byte, some return address here, and then the cache miss and so on. Those are very low level API that we provide here for the software guys to implement this cache strategy. At the other ends, we also provide what we call the high level API. The high level APIs here, we define that. Let's define, okay, given me some heading, some definition in the sp_h.h, sp_cache.h, where I define a load and a store. Loading is that I read cache, SPE cache read some address, right? And read some data out of cache here. And here is cache write. I will write some data, some piece of data here in the cache. And then when I refer to in my main programs, right? On the SPE program, when I refer to, I do the load, I read something and see it here, and I store C into some destination. That's it. We make the scheme like, very, very complicated. But you as a programmer, you're dealing with only definition of this. You have to define these guys here. And then when you use it, you need to load and store the cache. Okay? We hide all of these details of DMA and all of the rest of the complexity of DMA. On the large single SP programming models, we know that we have a code segment, we have the data segment, and we know the size of the programs. Each of the segment we know ahead of the size, right? When we sum up those size, we say, wow, the adding to the summations, the sum of the size of all my segments exceeding 256 KB. Can I break up those size? Can I break them up and in such a way that I can load them, one of them, two of them, or three of them on the same location using the overlay techniques? This overlay approach is not new. We're dealing with the 64 KB memories when we invent the power the first PC. Then we have to load a program larger than 64 KB or 128 KB or larger than 256 KB. What we doing? What we did then, we break the code into small pieces. We call segment, right? And we look at if they're independent to each other. Do they refer to each other? Reserve a specific address location, a segment of address space into memories, and loading those segments only when we need it, instead of loading the whole program when we start the program. The same concept right here in the self programming environment. When you run an SPE programs, when you load a program, you load everything. That's why you have so large, right? If you have your large address space, you cannot fit the program into the local store. Break them up into small pieces. For example, in this case, we break the program into different functions, A, B, C, D, E, and F, and the main program. The main programs sort of like the root segment has to be there all the time. That we have to do that, right? So main, the lower here, the main function main and F somehow go together. We can load the main program and the F functions into this segment over here anytime that we need them. Main always resident into the local store memories, and F will be loaded into this segment here. And then on this segment over here, we can define the load point for the function B or C, so we can load either B or C when we need B or C. And this segment here, we define the load point here, so we can load the SPE function A, D, or E. So we load this segment. Breaking up program into various segments, define the load points for those segments, and overlay those segments loading together. How difficult it is, you will see. Okay, when you see later on when we cover the overlay. An example on showing this chart over here, we have two overlay regions. We call the region 1, region 2. Region 1, we load the segments of all of the text. And segment 2, data, text, and object, and so on. Segment 2 again, okay, on the E executable maybe, yeah, objects and E format. And then the overlay is region 2, we load the segment 1 and segment 2 on the B and C and so on. So using the features, the features provided by the SPU linker here, we can feed the linker the data from this linker script and ask the SPU linker link my segments in such a way that I can load the segment here only when I need it, and it's very specific in the starting from the address defined by the overlay regions that I define. This overlay manager will oversee, manage, and loading all of these segments for you. The other way we look at, on the system memory, you have a program, right? And then the program, you can divide it into different code and data segment again, and you can queue them up. And then depending on the execution of the SP kernel, this is the SP kernel that you provide. Right? This is not a Linux kernel and OS kernel. This is a small program that running in an SPE program, running on an SPE, control the execution of those jobs here. It's running on looking for the code for the segment N and data N, go here asking, request the DMA, the code N and code for the data of N, and then running that, executed one, and then following through this job queue. We're also talking about another techniques that allow you to hide the latency. These techniques here we call the double buffering. In your traditional programming model, if you want to working with a large set of data or a set of data, but you want to continuously access the data in such a way that any time that you need the data, you have it. You can either load the data into a single buffer and accessing the buffer one at a time, right? Or you load the data in two buffers, break up the data into two buffers, right? And then accessing the buffer, and then accessing the buffer one, get the data, process the data, working with that data, and accessing the second buffer, working on, and then accessing back to buffer one. You can do that providing that you loaded the data into the buffer one and buffer two the first time, right? If we go ahead and say that, okay, now let me start my task. Before I start doing anything, let me load the data into buffer one, and then also load the data into buffer two. While I'm waiting for the data in buffer one, buffer two, I have to spend some time waiting, right? And then once I get the data on the buffer one, I'm processing the data. I finish processing the data, I get out. Before I get out, I initiate another request for the data on the buffer one. So that activity is going on now. I switch to my buffer two, I work on my buffer two, write the data, and now I have the data in buffer two, I'm working on. When I finish, before getting out of buffer two, initiate another request for the data, and then switch back on the buffer one. I switch back and forth, right? So that I always guarantee that I have the piece of data that needed. Some of you may subject, what happened if I have a different set of data or my data take longer on the buffer one or buffer two? Possible. You can make it double buffer, triple buffer, or multi-buffering. Right? Your buffer is where? Your buffer is down the local store. What is the drawback on that? The drawback on that scheme is memory constraint again, right? You have 256 KB. No matter what scheme you do and you apply, you still have to sacrifice certain space down there, right, to implement your scheme. Multi-buffering, double bufferings, or you're doing some software cache, it's still costing sometimes. It's costing some space. You're trading space for times. Okay, and the CSOF, we define this structure here, so you don't have to resolve the symbol by yourself. We define on the effective address over here. We define the structures. We call the card here G_full 512, and then on the local store, we may refer. This is effective address resolution or something we call EAR. We refer to this one as EAR _G_full structure. And down these programs, we refer that one is card as a local _full 512. So once we define these structures as a CSOF, EAR, we can refer, and we use this structure here. We demate the transaction in between those two locations without worrying about who is the effective address, who is the local store, right? Remember when we do the MFC get, MFC put, we need to know, we need to supply the local store address, the effective address, the size, and the tab, right? Some things that we need to, but the two address we have to supply is those guys. And this in this mechanism, in this implementation, you don't have to. Okay. Parallel programming models. This is traditional parallel programming models in your existing architectures, also applied to this cell environment as well. This is based on the interacting of the single SPE programs. We implement the parallel SPE programs here. Synchronization mechanism, we provide you the MFC atomic update commands. Remember when we draw the architectures of the MFC, we have various components. The MFC, remember, we have the MMU, we have the atomic. Atomic would handle the cache coherency for us. The MMU is doing the memory address translation units for us, right? And the action with some buffers in there, we use for the mailbox, we use for the buffers. Very simple, very neat organizations. And here it is showing that we use the cache line based MFC atomic update and mechanism, and that one was implemented in the MFC. We use the mailbox in there. We use signal notification registers and events interrupts. We handle all of those, right? Even any interrupts can be handled by the SPE and then transferred back to the PPE to handle it. If we have all of those interrupt handlers, we run on the PPE. Share memory, we can use the share memories processor and multiprocessor environments. In this scheme, the memories of the EA can be shared, or a segment or a address space and the EA can be reserved, can be shared and synchronized. The accessing mechanism will be synchronized by a typical synchronization mechanism. Okay. Compiler OpenMP support. We use the OpenMP here to provide the parallelisms for the SMP systems where we connect those BEs, CBE together. Okay, and we use MPI, message passing interfaces, protocols to support the clustering. Both the OpenMP and MPI will be available in the SDK 3.0. Okay. Message passing, we use MPI. Okay, message passing here. And one of the model we would like to touch about, spend some time here is the streaming model. And this model here, we assume that we have a set of input, right? We call it in I0, I1, I2, I3, I4, I5. Our data split into a different set of inputs here. And then the applications or the programs running on this memory here, okay, can send the data down for this SPE program. Okay, SPE programs here receive the I0, the first SPE receive the first set of data, processing the data and send it back. At the same time, the data I1 will send out to the SPE1 and then processing and send it back. At the same time, I3, I4, I5 will be sent out to the SPE3 and 4 and 5, right? So what we're doing is that we break up a set of data into small pieces, streaming down the set of data down to different SPE, and have the SPE perform those functions whatsoever, irrespective of the time. We don't care about the times. When we finish, send it back, get it out, O1, O2, O3, whatever, and then we process another set of data. That's how we perform the matrix multiplication. We subdivide the matrix into submatrices, and we do the performance, into pieces, and then we send out the data. The same SPU program, we design on SPE 0, 1, 2, 3, depending how we create a thread. We create a thread, feeding the data, giving some pointers to some address space, point this address of the set of data here, this data structure, get that address, DMA the data down to the SPE, and then perform. Another model is that if we know sometimes, if we know ahead of times, there is the completions times of our task of our SPE, we can implement something like the pipeline model, where we said, okay, I bring my data down to the first SPE, let it finish and move and send the data to resolve to the SPE, the next SPE. That SPE finish, working that one finish, send it to next SPE, and send to next SPE, the next SPE. Very beautiful concept, right? Dangerous, because we need to know when these guys finish, when the first SPE 0 finish, when the second SPE when the second SPE finish. We want one of the advantage of the SPE is that is what the times. We always want to know the completion time, the given, what we call the terminology here, the time to response, or the time, a real-time response, right? Always we guarantee the same response time every time. Okay, if we can do that, we can guarantee that one. This scheme is very good for you. Multitasking, we can break up again at the Linux level, or at the either at the open system at the kernel levels, or at the user space level here. We can break up our task or our workload into different tasks. We can task A, B, C, and D over here. Associated with each task, we have an event, and we have a queue of events here. And depending on the occurrence of this event, and we run that task. All right. So we need to have some program we call the event dispatcher. Similarly to what we had before, like some kernel, some the SPE kernels, which is an SPE program, just a control program to manage those events or to control the events here. All right, and control events, recognize events when the events happen, fill that events, and dispatch the task to serve that events. Self-managed multitasking. Again, we have an SPE kernels running here, and the job queues, which queuing a number of tasks, and based on the events happens now in the SPE kernels here, we can download, DMA the data, the code down to the SPE and run it through. Multitasking SPE kernel manage. This is explanations of what I will just describe. Okay. Some of the programming models here reduce development costs while achieving higher performance. This is true for the software cache. This is true for the multi-buffering schemes. And then some of these frameworks we provide here we use will be helpful to your productivities and to your time to solutions. Developing your code is a lot quicker. The models we propose here is not only models, right? And we discuss this model applicables only in the environment where we have a cell BE, right? We have a 1 PPE, a SPE, or we have a 2 PPE, 16 SPE, right? What happens in the environment where you have a system, traditional system, running and using the cell accelerator? Cell is an accelerator. You have to come up with that model as well. What happens if that traditional CPU or traditional PC or traditional system was running fully loaded, handling database, feeding data from your financial services or so on, and you have to handle different I/O devices and bringing the data in? That model is not addressed in here, right? How do we feed that data? How the data coming in through traditional CPU, send it down to the SPE, one of our SPE, one of our PPE, and then send it down to the SPE. And what happens if you integrate or you hook up and you build a cluster of those traditional CPU together and use the cell here as an accelerators, one or more or 10, whatever, a number of cells here is an accelerators, right? Performance very specific functions, rendering an image, processing a set of financial data, your stock options, for example, right? Look at the hedge funds, so you can build up your funds today based on the data, on the real time data. So this sort of accelerators models is existing now. We call the hybrid model, and those are not addressed in here. Questions? We do that now. We build some model. We call the Accelerated Libraries Framework, ALF. Okay, and that framework was introduced in SDK 2.0, addressing the situation where you have to support a hybrid model is between a traditional CPU and a cell as an accelerator. Okay, we may not go into the detail of that models because it's still working on, and then it's a lot of details involved that one. But that models. Let me ask you a question. What do you think about what are the requirements that you fit to that model? Let's say that you have an application running on your main x86 based machine, right? On your traditional CPU, one application running that one, and you want to send some piece of code out here, so you can accelerate it on CLBE. What do you think you need to do? What do you want this cell accelerator to do? What do you want him doing? The task, you have to bracket the task, your big task over here into small tasks, you can send it out. Application partitioning, right? You have to partition your application into pieces. Same model here, but on the other hand, partitioning your data, your application into small segments or small pieces, and then move it, which pieces go to this SPU, or which piece go to this PPU, or which piece go to this cell. Because you may have more than one cell accelerators, right? More than one PS3 here. Nobody is saying that you cannot build a cluster with PS3, right? And if you follow, some of the online news lately, the past week or so, some students only build a cluster of PS3. And that cluster of PS3, if you couple that cluster of PS3 with a system, a cluster of traditional CPU, you build a supercomputing center, or you build a very, very powerful system here. Application partitioning is one area, right? Application partitioning, you also have to handle a lot of data coming in as well. You do the data partitioning. So you have to think about the scheme of your partitioning your data as well. And then receiving the data, right? You are just computational, right? You receive data. You, as a programmer, you have to think about that framework. ALF has to provide you some things that you can fit the data. Fit it easily. You're not going out here, you're not, as a programmer, you're not doing the DMA by yourself. You issue one DMA and go get data DMA, this, that. You build a list of data, whatever, or you do the software cache to do it better. But that framework has to provide it. Those are the features of the ALF, you will see. Data partitioning, application partitionings, hiding away the DMAs, doing double bufferings. It is now doing the double buffering. In the future, it will do a multi-buffering as well for you. And of course, do a DMA list. I think that we cover the DMA list tomorrow. Those are kind of programming models that IBM is working on. Okay, we're not stopping at those programming models. And you, as a programmer, when you're working on different models, you may see this model here. Talk about this model. This model does not fit to my environment here. I mean, it's something else. And that's coming up, with the parallel programming aspect that you're working on, right? And so you can see that. Is there anything that I had before, or is there anything that in my course and my project here I can use this, or should I invent something else? And nobody stopped you to invent anything else besides this model. These are just our model. We think we have this environment, we have this local store, we have an effective address, stored here, and we come up with some scheme that we feel that's comfortable. But as we're dealing with it, going out and we expand the horizon of these architectures and features, we encounter more questions. Your questions on how to handle your question on the hybrid models. It's coming out the hybrid models that we discussed. But you said you thought about it. Okay, this model is fine, but I have a traditional CPU, the machine I run. I mean, I can hook up this cell here, this PS3. How do I do that? The hybrid model is a very important model. Nobody's going to use this model by itself except me and you and some of the games player, right? But when you put together a real world and build a real super center, okay, And yes, it's possible, potentially, and that's what we're doing now. IBM is doing with the Los Alamos labs on the Roadrunner projects. It does not to stop you to build your own projects here with the cluster of the PS3 or cluster of the cell plate. Okay, software managed cache. We mentioned this one is the techniques that allow you to reserve or allocate a segment down your local store and use it as a cache. And you manage it. You as a programmer manage it. You may ask why you ask me to do so many things. I write programs, right? And I have to write the cache too. I manage the cache too. This is hardware design. This machine was designed by the hardware guys, and those hardware guys give you a lot of freedom. The software guy said that, okay, either I take these freedoms or not. I'm waiting for AOF and some other models to help me better. But for those of you that really want to get to the lower levels, that want to control, okay, give that 256 KB, right? You can control that one. I have my own cache here. I have a 2 cache here. I have a 3 cache. I have a number of cache I can play with. Every time that I add some cache in, right, I can see some improvement. That was proven at some program that we have the demo here. The demo we build with 3 cache, 4 cache, 5 cache, and so on. And every time that we add some more cache, right, the performance improve, get jump another 5-fold, another 5x, another 6x, whatever, right? Because what is boiling down, if we relocate it or we make the data available to our CPU, to our SPU, then we should load and store and run. That's all we do. Right? We don't have to pay any latency in terms of memory latency. The question is that if you reserve one SPE, the local store of one SPE is a cache, right? And let the other SPE access that cache. How efficient it is. If you reserve one SPE as a cache, that local store, in order to access that local store from any SPE, you have to provide some SPE IDs to create the thread, right? And you use that SPE to go over there, go over the EA address and fetch the data, go to that route, because you have the memory map, the data from the local store, you map the EA and so on, right? So efficiency, implementation-wise, nobody can say no, because you can access a local space in this LSE on the SPE 0 here can be accessed by SPE 1. Nobody said no. But since we say that we use the SPE as a computational engine, so we prefer to use that way. Okay. Here's the basic cache concepts. Everybody familiar with this one? Skip. Going through. Cache line. Right? Okay. We use the cache, we have the size, and all these end weight, end set, how many weight, we partition the cache line, the set. I don't remember. I mean, when we look at the new architectures, if you are not the designer, right, you are just a programmer. When you look at the description and specification of the new Intel CPU and so on, you look at the cache, you set the size, the cache size, then what? Yeah, you sit down your program, right? And here you say that, okay, I have to know a little bit about that organization. I have to know a little bit about, what does it mean to me? The fully associative mappings, right? And then the end-weight set associative mapping here. We have direct mappings. Okay, we map everything to cache line, and we fully associate mappings where we map any memory location to a cache line. Your cache consists of a number of cache lines, right? Okay, so you have that cache line, and how you organize those cache lines in group, in single one, or how you map that cache line or a group of cache line to a set of locations in your memory here. So you cache the buffers or the data on that memory into this cache line, and that's allow you to access the cache. Okay. This one is applicable to the local store only. And these benefits are the same benefits that you observe when you have a hardware cache. Simplifies programming models. From your load and store effective address model can be used, decrease the time to port to SPE, The advantage of locality of reference, that's the traditional one, that's why we have the cache. Come on, right? Can be easily optimized to match data access patterns. This is new here, right? This is software managed cache. Provide ability to apply sophisticated replacement algorithms and so on. Do we invent this software managed cache? I don't think so. If you search through Google, a lot of people work in a software managed cache, right? This is not IBM's inventions. This is the one that invented by many technical in the technical communities. We saw the concepts, the fit environment here, we use it. Right, so we suggest you, if you see something that's new or that's been used or whatever, you can retrofit the concepts out to here in the cell, use it, right? As long as you can exploit certain features of cell here. We exploit this one because we say that we want to prefetch the data, okay? We need to have data to supply that SPU. We want to prefetch it. How do we do? Provide a cache, that's it. And where do we get the cache? We go now searching for how do we implement the cache? This cache concept has been discussed in IBM like 4 or 5 years since the beginning. But just actually implemented and done and released on the SDK 2.0 only. So to see how long does it take, a couple of years, 3 or 4 years to implement this scheme here. We talk about a lot of software cache in the SDK 1.0, but only in the 2.0 we have actual implementation, and we do have some example to show you. Okay. The heading file is the cache minus API. I think cache underscore cache minus API.h here, and in here the cache attributes consist of name, associativity, the line size, the read onlys, or the read and write. Okay, the type of data object to cache, integers, chars, float, and so on, and the number of sets. User can define the multiple cache by redefining the attributes. Every definitions, every software cache has to be defined by including the cache API here and then the attributes. You want the second software cache, you repeat this section here, right? The cache API and the attributes and so on. So you can define n software cache as you want to. The attributes are cache type, the type of your data, right? The name of your cache, and then the size, the sets, the n-way, the type, read and write, or read only, the read x4. This one is mean that each time you do a read, you read the 4 words here, and then the cache stats give you the statistic of the cache. Defining a cache, I define a cache name, my cache type, my type is T, 4-way, 8 sets, read and write, cache line is 9, and then the start enables and included the cache API. Cache read, cache write, cache touch, wait, read and write. And these are the interface. To make life simple and easier for you to use these features, you are required only to supply the type and the name of the cache only. All of the rest, the set, the word, whatever, leave it to us. We set a default. You can of course change, but if you don't want to specify anything, leave it to us. We define default for you, and the replacement algorithms, first in, first out, and so on like that, we define it for you, and you just care about the name and the type of your cache only. Okay, here is an example. We use the cache to swap 2 values. Okay, and we use the cache read. Cache read here is an interface provided by the software cache utilities, right? And cache the effective address 8 over here. Read the cache into address 8. Read from the cache specified by my items. The name of the cache is my underscore items into address 8. Okay, and then read again my items in the bit here, and then write 8 over here, 8 into the address into the cache, my items also to the address effective address A underscore bit here, and then write B into A. So what we did, we read value 8 out, we read B, we put B into we put A into B, we put B into A. We swap 2 values. behind the scene, what we're actually doing. We have to issue an MFC something, put right, or get something, go to effective address A or B, get that data, bring it down to the local store program, to the SPU, exchange the data, switch that one, MFC put back. A number of MFC command we have to issue. Here we just do cache read and cache write. That's it. Right back. Algorithms. Some of these algorithms here, same thing. So we talked about in the hardware when we learn our architecture class. Same thing. This is the graph, a chart showing the implementation of the cache, the log and modify and valid. Some directories of your cache here, the lookup, form the index, and so on. Just the kind of performance-wise. Okay, this is kind of showing the size of the cache line here, the line size, and then the hit rate. Okay, and applicable to the program quick sort, hit rate versus the line size. And the cache size is about 8K, 16K, 32K, 64K, 128K. So as we can see, the hit rate about from 75% improved to 85, something almost 82%, very high rate. However, is with the 32 byte cache, the line size, and then we go on as further the lines getting longer and longer or getting bigger and bigger, we see the performance really decrease. So depending on if you have a small line size, 128 or something, and this line over here, that's the line size of our cache. Okay, you will see some difference improvements in terms of the cache size. Okay, the hit rate improve a little bit with the large 128 KB cache size. 128 KB, that's half of my local store. Would you dedicate a half your local store to your cache? No way, my friend, right? I mean, maybe 16K to byte or something like that, right? And 6K. So again, different programs, different approach, different techniques, different results. This is the quick sort runtime versus line size, and this is the hit rate versus the line size, and different heap sort, right? This heap sort behavior more or less based on the cache size as well. We can see that these guys, the hit rate jump between 76, 77% or 80 something percent. Okay. Runtime versus the line size again, and cache start. The set, right? To set organize the cache line in terms of set. How many sets do we have? We have 8 sets, 7 here, or 1 or 2 or whatever. Differ a little bit, right? The hit rate, hit percentage here, hit rate almost the same thing, 94% or 91%, based on the read and write. The set here on the quick sort with the prefetch and write buffers, almost the same. So experience with your programs, and then with your, all right, let's go. Any questions before we close up here? Okay, ladies and gentlemen, wrap it up and let's go to the labs.